Gomez-Rey, and this is my physics lab report on oscillations. All right, so the goal of this lab report is to compare and contrast the predicted motion and observe the motion of the mass attached to a spring. And we're going to find kinetic, gravitational, spring potential, and total energy. And the results should be that the predicted and the observed motion should be similar in the x and the y axis, but the total change should be 0 of energy. All right, so the main concepts is that we're going to need the net force of the object, which in this case will be the change in momentum over the change in time, because the change in momentum will be seen from the mass of the spring changing. And then we're going to need the velocity update formula and the position update formula. And then we're going to need the energy principles, which in this case, the change in energy is equal to the total work, which will be the work of the system, the work of the surroundings. And then we're going to need the energies to actually find the work, which will be kinetic, potential of the spring, and potential of the gravity. All right, so we actually need to define what our system and what our surroundings are. So in this case, our systems will be the earth, the spring, and the mass, which is why we need gravitational potential, spring potential, and kinetic energy. And then our surroundings will be nothing, which means that our work in the surroundings will be equal to 0, which means that they won't have effect on the actual system. All right, and then also our system will be in static equilibrium, which means that the F net will have to equal 0, which means that the force of gravity and the force of spring will have to equal 0, as shown here in the free body diagram. They're equal to each other, so they will cancel out and be 0. Gravity is going in the y direction, spring is going in the positive y direction, and then here we see our equation for the change in energy in the system. Here is my tracker model video, if it plays. Yep, you can see how it changes there, and I'm actually getting all of the center of the mass and tracking it. And then from the tracker videos, we see the frame rate, the mass object, and then our observations with the initial time, initial position, initial velocity, and final time. As shown here, this is it moving over time. As you can see, it's going like up and making crests. And then the initial conditions from the video, we see the mass of the ball, position, and velocity, and the time. And then the gravity constant is already given, which is 9.8. And then we need to actually find the spring constant, which I use these equations shown on the right. And then also we need to find the relaxed length of the spring, which is also the equation shown on the right. And then we also need to show the distance from the relaxed spring state, which shows this in the coding. And then the actual energies, which again, we are finding the kinetic, gravitational potential, spring potential, and the total energy, which is shown here as 0, because overall the total energy or the change in energy will be 0. And then we see that we need to find the net force, the velocity update formula, velocity update, and the new position. We can see this using the K that we found and the actual F spring and F grav, which we get from the K and the gravity constant. And then we need to create an actual while loop for the code to go on for a couple times so we can see the actual change in momentum. And then we're comparing it here to the tracker, to the actual computational. And then these are the results of the graphs. We see here in the middle that we see that the yellow is 0, as in the line of the 0. This is because the total energy will be equal to 0 once you add up all the K, UG, and U spring. And then the analysis and the errors, we see that the energy and time graph, as U increases, the change in potential gravity also will decrease, and then vice versa. So if potential gravity increases, then potential of spring will decrease. And then the model actually accurately shows the x in time, but it doesn't actually accurately show the y time, because in the errors we see that the computational does not take into consideration of the drag force and other energies that could take effect, like thermal and rotational kinetic. And then the tracker may also not track the exact center of mass, which is hard to track through a video. So then what does this mean? So as shown at the beginning of the results in the introduction, we see that the sum of the potential gravity, potential spring, and kinetic energy will equal 0, as shown with the yellow line. And then the sum shows that nothing from the surroundings does actual work on the system, which proves our initial statement. And then we see the oscillation periods, which are shown by the crest as shown before. And then to find the average oscillation period, we need to find the sum of the two crests divided by 2. And then in this case, we can find the x position of the oscillation, the y position, and then the difference. So what does the difference mean? It could be caused by incorrect tracking of the center of mass of the object, drag forces acting on the object that are not taken into consideration, and then also the calculation of the spring constant, K depends on the oscillation period. So if K is not correctly, the oscillation period could be wrong. And then we have spring force and spring potential energy, which could also impact these. So that's it. Thank you so much.